Does anybody have any questions before we get started? There were apparently a little bit of confusion in regard to which seat people are sitting in. Hopefully you'll see yourself on this sheet right here. Can you take one, please? Thank you. A couple of issues. Sometime in the next couple of lectures, instead of me standing here, Dr. Chin's going to be standing here. We're going to try to trade off back and forth. I don't know whether the trade-off will take place Monday or sometime next week, but it will take off shortly, and then we'll kind of bounce back and forth. I don't believe I posted office hours yet. My office hours are Monday, Wednesday, and Friday at 11, or by appointment, or you're welcome to stop by any time that the door is open. And if I'm not busy, I'll try to accommodate you. And Dr. Chan, Monday, Wednesday, and Friday at 3:30. Okay. And the TAs will also set up some office hours, and we'll probably let you know sometime next week what hours they set up. If you have homework assignments, feel free to bring them by after class. But they will be accepted up until 5 o'clock. There's a box with a slot in it in the lab. If you choose to bring them by after class, slip them in that box in the lab, and the graders will pick them up probably sometime this evening. Okay. Today I'd like to talk about basic logic circuits. I talk a little bit about completeness of logic families. I'll talk about different logic design styles, and then we'll start looking at improving device models. Of course, we haven't given a device model yet, so we'll give that first as well. Review from last time, we saw that the integrated circuit was invented by young engineers that are around 30 years old in 1959. The two people were Jack Kilby and Bob Noyce. They did it independently at two different companies. So basic logic circuits. That little puzzle again that we're trying to get put together. So we'll spend a little bit of time talking about circuits today, and we'll talk a little bit about device modeling today. So a couple of pieces of this puzzle we'll try to look at today. We'll present a brief description of logic circuits based on simple models initially, and a qualitative description of the process. We'll later discuss process technology needed to develop better models. It's hard to get a better model unless just saying, oh, here it is. We'll try to discuss the technology so we can see where better models come from. And then later we'll develop even more in-depth logic circuits and even better device models. So that's kind of how we're heading here. Of the different models we're going to look at, they're going to vary in complexity, accuracy, in insight that's available from the models, and in the application that you're looking at. Models that might be good for a digital application may not be particularly useful for an analog application, and vice versa, even though we use the same transistors. We will always try to use the simplest model that can give acceptable results for a given application. Well, that's pretty easy then. Take the simplest model we can get and use it. The challenge, of course, is verifying that that model is good enough for that application. So here's a qualitative discussion of the operation of an N-channel transistor. And up to this point in time, we've been looking at a transistor from a top view. And we look at it as an intersection of two polygons. One of the polygons is a gate polygon, and one is an active polygon. And we said that the transistor was really in this region here where the two intersect. And everything else was just overhead needed to separate the devices and get connection to the devices. If you now take that wafer we handed around and flip it on the side and look at a cross section of this transistor, and these are approximately aligned right here. This edge is aligned here, and this edge is aligned here. So this distance from here to here is the same as the distance from here to here. What we'll see in a cross section is N-type diffusion right here, and an N-type diffusion here. One is called the drain and one is called the source. From this picture, they're symmetric, and the devices we'll be working with in the laboratory, they will also be symmetric. Makes no difference what you call the drain and what you call the source. They're made the same way. And this gate region is going to sit on top of a little bit of an insulator. That's a cross-section of the device. As far as the model is concerned, or schematic is concerned, the red region is called the gate, and then the two regions on the side are called the drain and the source. So this is one symbol that's used for an N-channel transistor. I'm also going to try to use color designations throughout the course. This is probably the color designations I'll use. If I have a doped semiconductor region, and what a doped semiconductor region is, we talked about silicon crystals earlier, and then we put a small number of impurities in that crystal to dope it. We'll talk about how many we put in. We don't put very many in. If we put a very small number in, I'll have N-type impurities. I'll use light green. More N-type impurities, I'll use darker green. If it's a very small number of P-type impurities, I'll use light yellow. I'll use a darker yellow if it's a higher concentration of impurities. Right now, the insulator, I'm going to use gold, and then the red that we use for the gate, is going to be used for the gate, and it's typically made of polysilicon. So that's a top view and a cross-sectional view of the transistor. As we said, they align this way. The designer always works with the top view. You don't have to know too much about what goes on in the cross-sectional view. The people that develop the devices and develop the process worry more about what goes on in the cross-sectional view. But what goes on in the cross-sectional view is reflected in the models we have in our circuit schematics. So the behavioral level description that we have right now is if the gate to source voltage is large, so you put a voltage from gate to source and it's a large voltage, there's a short circuit that exists between drain and source. And if the gate to source voltage is small, there's an open circuit between drain and source. So that means that this gate to source voltage that we put on determines whether we have a switch closed or switch open between drain and source. That's a pretty simple model, isn't it? So here's the gate to source voltage we apply. And if it's small, there's an open circuit here. If it's large, there's a short circuit. Right now, let's not worry about how large is large or how small is small. We'll worry about that later. When we talk about Boolean levels, and Boolean levels are typically in the voltage domain. So if this is the voltage axis between 0 and the supply voltage to our circuit, there will be a range of voltages that are near the supply voltage that we refer to as a Boolean 1. So the Boolean variable is G in this case, and G is equal to 1. And there are a range of voltages near 0 that we will refer to Boolean 0. And there's a whole bunch of voltages in between, and at this point in time, we won't even try to make an assignment of a Boolean value to the voltages in between. Okay. So if you look at the voltage axis is continuous. If you look at the Boolean axis, it's two-valued, either a 0 or a 1. So it's discrete. Most logic circuits are characterized by the relationship between the Boolean input to the circuit and the Boolean output to the circuit. But those Boolean inputs and Boolean outputs come from continuous voltages that we apply at the input or we measure at the output. Here's an equivalent circuit for the N-channel MOSFET. If the gate voltage is low, that is the Boolean input is 0, the switch is open. And if the gate voltage is high, the switch is closed. Gate voltage high being a Boolean 1 input. Now, I've chosen to give this model in terms of Boolean signal reference relative to ground, and I'm assuming that the source of this N-channel transistor is also connected to ground in this model. Source is assumed connected to ground or close to ground. This is the first model we have for the N-channel MOSFET, the switch level model. It's an ideal switch level model of the MOSFET. I'm not crazy about this model because this model depends upon where we collect the source of the transistor. We're connecting the source to a 0 volt or a Boolean 0. We can also describe this model mathematically. If the switch is open, the drain current is equal to 0. And that's if VGS is low. And VDS is equal to 0 if VGS is high. So this is a mathematical model for the transistor. So we got a switch level model described mathematically here for the transistor. Notice we're giving IV characteristics for the transistor here in this model. P-channel transistor operates in a very similar way. Instead of having a P-type substrate, we start out with an N-type substrate or region here. And then we have P diffusions occurring on both sides. And those P diffusions form the drain and the source of the device. Of course, the top view of the P-channel transistor looks very similar to that of the N-channel transistor. The only difference is I've got yellow instead of red shown here to indicate that it's P-type rather than N-type diffusions. So both P-channel and N-channel transistors are formed by the intersection of a gate region and a diffuse region. The symbol for P-channel MOSFET that I'm introducing here is shown on the upper right. Some people say we put a bubble on the gate symbol to change it from an N-channel to a P-channel device. I should point out that I'll try to be careful and tell you whether I have an N-channel or a P-channel transistor. But it is not uncommon to see circuit schematics published where the author does not tell you whether it's an N-channel or a P-channel transistor. They use the previous symbol for both. This is the symbol we had for an N-channel transistor, and some authors choose to use that for both N and Ps. It might appear a little bit disturbing that the author doesn't tell you whether it's an N or a P. But the philosophy is pretty much the following. If you're knowledgeable enough to have the ability to understand how the circuit operates, you will pretty quickly know whether the transistor is an N-channel or a P-channel transistor, and hence it's not necessary to make that designation. Does that make sense? Okay. So don't get confused if occasionally you see N or P-channel transistors without using different symbols for the devices. Again, there's alignment in the cross section and the top views of the gate and the source and the drain. I should point out that this cross section I'm referring to here is a cross section along this line. I could look at a cross section along this line, and that cross section will look different. We will talk about that later. when we talk about how these transistors are actually put together. So this is a cross section along this horizontal cross section line, right in the middle here. Yes?
Just a quick reference of that. Is this distance going across the screen the length of
Yes.
the semiconductor?
This distance here is the length of the transistor.
Okay.
And you can control it. In the laboratory, we control these dimensions. Well, it's the drawn length. The actual length we said earlier was a little bit less than this, but that's the drawn length.
So is the length only dependent on the gate then?
The length is only dependent upon the gate. The gate determines the length, and the active determines the width. We have design rules. The design rule says you must have the source extend so far beyond the gate. That way the gate determines the length. And the design rules say that the gate has to extend so far beyond the diffusion region, and that way the diffusion region determines the width. Okay. Furthermore, it won't work if you don't do that anyway. Again, as for the N-channel device, there's complete symmetry in this model, as will be for the device we look at throughout the course, between the drain and the source. So again, it appears to make no difference what you call the drain and what you call the source. However, when we look at our device models, we will see that depending on which way we orient them, it's more convenient to call one side the drain and one side the source. Right now, we don't worry about that. Behavioral description of this device. If VGS is large in magnitude, so large and negative for the P-channel device, a short circuit exists between the drain and source. And if VGS is small, near zero, an open circuit exists between the drain and source. Now here's where it gets a little bit tedious. I'm going to now assume that the source of the P-channel transistor in our logic circuits is connected to near VDD, near a Boolean 1. Again, we may relax that later. We'll have better models and we won't have to make this assumption. But I'm going to assume that the source is connected to near VDD, near a Boolean 1. And here's my model then. If the gate to source voltage is large in magnitude, that is big and negative, it's a short circuit between drain and source. And if the magnitude of the voltage between the gate and the source is near zero, we'll assume there's an open circuit between the drain and the source. Now notice that the opposite thing has happened for this P-channel device than the N-channel device. When the Boolean input was 0 for the N-channel device, it was open. When the Boolean input was 0 for the P-channel device, it's a short. So opposite characteristics. This is under the assumption right now that the sources are connected to near ground for the N-channel devices and near VDD for the P-channel devices. So this is the first model we have for the P-channel MOSFET. Mathematically, the drain current is 0 if VG is high, the gate voltage is high, that's when it was open, or the magnitude of VGS is small. And likewise, the drain to source voltage is 0 when G is equal to 0. That is, if the gate voltage is low. Now, if the gate voltage is low and the source is up at VDD, that means the magnitude of the gate to source voltage is high, and it's negative. So if VDS equals 0, if the magnitude of VGS is large. So if you think of the model for the N-channel and the P-channel device, in both cases, it's a short circuit, and the magnitude of the gate to source voltage is large, and it's an open circuit if the magnitude of the gate to source voltage is small. So here's a comparison then of the switch level models. We call these a switch level model for the N-channel transistor and the P-channel transistor. And we see that they have complementary operation. Let's now look at logic circuits. So now I'm going to connect some transistors together and see what happens when we connect them together. So I have an N-channel transistor and a P-channel transistor. We said the source of the P-channel transistor is going to connect near VDD, source of the N-channel transistor connected to ground. Drains of the two devices are connected together, the gates are connected together. Well, if that be a Boolean input A, we'll look and see what the output of the circuit looks like. So, I'm going to initially assume A is 1. If A is 1, this N-channel transistor will be in the conducting state. So this will be a short circuit. And if A is 1, the P-channel transistor will be in the off state. So the switch will be open. And so if you look at that circuit then, there's a short between the output and ground. So the Boolean output will be a 0. So what have we formed? We've formed an invert, well, almost. When input is high, the output is low.
I'm not a game.
Yeah, and we have to go through and ask the question, what happens if the input is low? When the input is low, we'll show that there's a short between the output and VDD, and that's a Boolean 1, so the output is high. So we formed a NOT gate, or an inverter. Okay? And here's the truth table for that inverter. Look at this circuit. I'm going to take two N-channel transistors, I'm going to connect them in parallel. I'm going to take two P-channel transistors and connect them in series. These sources are both near ground. I'm going to argue that these sources are both near VDD. This one is connected to VDD. We're going to see when it matters, this one's connected near VDD as well. So let's see how this circuit performs. So I'm first going to put in a 0, 0 at the input. So I put a 0, 0 at the input. These two transistors are turned off. There's an open circuit here. And I put a Boolean 0 into the P-channel device. They're both turned on. So now I can see that there's a short circuit with this device model between the output and VDD. So the output is a what? A 1. So the output's a Boolean 1. I have 4 different inputs. I'm going to put now a 1 on A and a 0 on B. If there's a 1 on A, that's going to cause a short circuit on this transistor from here to ground. And if there's a 0 on B, this will be open. But likewise, if there's a 1 on A, this circuit will be open. And if there's a 0 on B, this one will be closed. So now you look at this circuit and we see that there's a path from C to ground, a short circuit path, then an open circuit path this way. So the output is a 0. So this is a Boolean 0. I'm going to next do 0 and 1. The circuit is basically symmetric or almost symmetric. So we put a 0 and 1 input. The output will also be a 0. I guess there's one more input, and the input I haven't looked at is both 1s. If there are both 1s, these will both be conducting, and these will both be non-conducting. So the output is a 0. So we can look at a truth table. And this is a truth table. So what have we formed? NOR, a 2-input NOR gate. Okay. Here's another circuit. I can do the same thing with this circuit and the switch level models we have. This is the truth table we will get. And this is recognized as a 2-input NAND gate. The approach can be extended an arbitrary number of inputs. We can put N-channel transistors in parallel and N P-channel transistors in series, and that will form an N-input NOR gate. And we can put N in series of the N's and and the P's in parallel, and that'll form a multiple input NAND gate. The family of N input NOR gates forms a complete logic family. I don't need NANDs to build logic circuits. The family of the N input NAND gates forms a complete logic family. I don't need NOR gates to build logic circuits. Having both AND gates, having both NAND gates and NOR gates available to build logic circuits is a luxury. Then I can choose which I want to work with. Well, we've gone a long ways today. With this switch level model, and with these two devices, if I put a bunch of them together, I can now implement any combinational logic function. Any combinational logic function. Go into a microcontroller and look at all of the complex, look at all the logic functions that are in there. I can implement them with these gates. If I had one flip-flop, and we could make a flip-flop pretty quickly as well, we'd have to have a slightly different model, but we could do that. If I add one flip-flop, I can easily create any flip-flop with that one flip-flop and some combinational gates. So if I just add one flip-flop, I can implement any sequential Boolean function. Wow. So we've made a lot of progress already. We won't talk about the flip-flop for a while. Flip-flops are easy to design, but we'll talk about those later in the course. We won't spend much time with them. There are also other methods for designing logic circuits. Some logic circuits are better than others. These multiple input NAND and NOR gates are used extensively when building digital circuits today. But there are also other logic circuits that are very useful as well, and sometimes offer advantages over the multiple input NAND and NOR gate approach. So I'll try to give some insight into why other logic styles evolve, what their benefits and limitations are, and then I will emphasize that in a large design, the designer will typically mix and match a whole bunch of different logic styles in one design, picking the particular logic style that is best suited for a particular part of that circuit. If you look at this inverter, we put some nomenclature on parts of the structure. This device on top, which is comprised of a P-channel transistor, is called a pull-up network. It tries to pull the output up to VDD. And that transistor on the bottom, which is comprised of an N-channel transistor, is called a pull-down network. It tries to pull the output down. If you look at this circuit structure here, you'll notice the circuit has an interesting property. And that is one and only one of these networks is conducting at the same time. Either the pull-up network is conducting and the pull-down network is open, or the pull-down network is conducting and the pull-up network is open. We will see later that we've actually implemented this Boolean function twice. We've implemented the Boolean function by using the pull-up network, and we've implemented the Boolean function using the pull-down network. This is a lot of transistor overhead that we have to implement a Boolean function twice. But there are some real interesting properties that we derived from implementing this Boolean function twice. Here was our two-input NOR gate. We can observe that the two P-channel transistors on top form a pull-up network, And the two N-channel transistors on the bottom form a pull-down network. And as for the previous structure, one and only one of these networks is connecting at the same time. Again, we implemented a Boolean function twice. Once in the pull-up network and the complement in the pull-down network. Two-input NAND gate. Same issue. We have a pull-up network and a pull-down network. Again, the pull-up network is comprised only of P's, the pull-down network only of N's. So now let's ask the question, what are behind below? What's the power dissipation? And how fast are these logic circuits? Those are probably three of the most important questions we ask when building a logic circuit. So with these models, what are behind below? They're Boolean 1 and 0, but in the voltage domain, 0 VDD. Okay. What's the power dissipation?
Something close to 0.
Why is it not 0?
Because there's a small amount of current that does actually go through the transistors.
In this model?
Yes. No.
No, not in this model. So, good observation. If you look at a better model for the devices, you might find a little bit of current flows. But in this model, there's no current that ever flows. Okay? So the power dissipation is 0. And how fast are they? Instantaneous. Wow, these are nice circuits. Behind, below go from 0 to VDD. No power dissipation, infinitely fast. Well, as was pointed out, there might be a little bit of power dissipation that we've neglected. And do you think they're infinitely fast? Probably not infinitely fast either. So the reason that we don't see the fact that there might be some power dissipation, and the reason we don't see a limitation on speed, is inherent in the models that we've used for the devices. That suggests that we need better models if we want to eventually see what the power dissipation is, what the speed is, or possibly what the logic levels are. Okay. So things look really good with this model, but we don't expect this to quite hold up. So these characteristics are really too good to be true. Now, if we go to an arbitrary pull-up network that's comprised only of p-channel devices, and an arbitrary pull-down network that's comprised only of n-channel devices, doesn't that have to be the parallel series combinations, and one and only one of these networks is conducted at the same time, then what are behind the goal going to be? One and only one of these networks conducted at the same time. 0 VDD again. Okay. And what's the power dissipation going to be with the models we have so far? What? 0. 0 power dissipation. And how fast is it going to be? Very fast, infinitely fast yet. Okay? So we've gone away from just multiple input NAND and OR gates now. We say any circuit that has pull-up networks with P's, pull-down networks with N, and one and only one of the networks is conducting inherits these three very desirable properties. These key characteristics are characteristics of static CMOS gates. And these are the properties that we have if the one and only one of the networks is pulling up at the same time. So let's now build some circuits. How many transistors are required to implement the function A and B bar bar or A bar and C? In a CMOS process, if static NAND and NOR gates are used. I'm going to assume the inputs that are available are the Boolean variables themselves, A, B, and C. Well, here's a brute force way to do it. I'm going to create A bar, and I'm going to, I don't have an AND gate yet, but I can take a NAND gate and an inverter to get an AND gate. So I have A bar, C ANDed together and inverted. This forms an AND gate. I can invert B and AND it with A, and I want to invert that, so I put that in here, and then those are ORed together. I don't have an OR gate, but I've got a NOR gate, so I can take a NOR gate and invert it, and I implement F. This is a brute force way to implement this Boolean function. If I do it this way, I have 5 levels of logic. The A signal has to propagate through 1, 2, 3, 4, 5 levels of logic until it gets the output. And I have 2 plus 2 is 4, plus 4 is 8, plus 4 is 12, plus 2 is 14, plus 4 is 18, plus 2 is 20 transistors to implement this circuit. Is that good or bad? Bad. There are 2 bad things about it. What are the 2 bad things about it?
Number of transistors.
Number of transistors and
It's slow.
well, right now we don't necessarily know it's going to be slow, but it will be because of the number of levels of logic, right? Yes?
Cost.
That drives the cost up.
And space.
The cost is related to the area, and the yield is also affected by it being big, right? So we implement functions like this, but this is not particularly attractive. Now, I can do some Boolean manipulations of this function. You've done those before by applying De Morgan's laws, for example. And it happens that this F is equal to A bar or B. So I can implement the same Boolean function. Here's A bar, and then a NOR gate inverter is an OR gate. And if I do this, I reduce it to 8 transistors, 3 levels of logic. This is a form of what we call logic optimization. In this case, I haven't described what my optimization goal is. I've just observed that I can cut the number of transistors and the number of levels of logic, and that's probably good. I could do optimization where I want to have only NAND gates. This has NOR gates involved. I could do logic optimization where I only have NOR gates and no NAND gates. I could have all kinds of different cost functions available for doing my logic optimization. I can write this Boolean function in a different form. This appears to be more complicated, but with NAND logic, I can implement this with 2 gates and 2 levels of logic, or a total of 6 transistors. So we went from 20 transistors and 5 levels of logic down to 6 transistors and 2 levels of logic. Big reduction. How about this function here? A exclusive OR B. That might be used just about as much as the NAND and the NOR functions. So let's look at a static CMOS implementation. We know A exclusive OR B is equal to A B bar or A bar B. Everybody remembers that, right? Okay. So we'll take the brute force approach again. And if I take the brute force approach, I can implement this exclusive OR gate like this. And I see that requires 5 levels of logic and 22 transistors. Okay. Is that good or bad? That's bad, because it's a real common function, and it requires lots of real estate to implement it. The delays will be unacceptable, but from this model, we can't see it. And the device count, well, I say it's too large. Have to be careful. It's only too large if we don't have a lower device count. If we need this functionality, this could be the lowest device count we could realize. It's certainly large, and since we use the function so often, we hope that we can get by with less devices. Here's another implementation of that same, this is a different function. This has 3 levels of logic and 16 transistors. If you take this circuit here, now this circuit here is different than the circuits are built of NAND and NOR gates. There's no NAND or NOR gates here. But I do have a network that serves a pull-down network comprised only of N-channel devices. And I have a network here comprised only of P-channel device that could serve as a pull-out. And if this had the property that one and only one of these networks is conducting at the same time, then we have rail-to-rail logic swings, we have infinite fast response, and we have zero power dissipation. You can show this also implements the function A and B or C and D bar. That was the example we had a bit ago. So instead of having 16 transistors and 3 levels of logic, we now have 8 transistors and 1 level of logic. This is termed a compound gate or a complex logic gate style. There's that pull-up network we saw. And there's the pull-down network. And you can show that one and only one of these networks is conducting at the same time. So these both implement static logic functions. To distinguish between these compound gates or complex gates, I'm going to refer to circuits that are comprised only of NAND and NOR gates as static CMOS logic. And I'm going to refer to circuits like this that have pull-up and pull-down networks, where we have logic functionality built into the pull-up and pull-down networks themselves. I'm going to refer to them as either compound gates or complex logic gates. They're really all static gates, but I'm going to only refer to those with NAND and NOR gates as static CMOS logic. So how can we build circuits using this complex logic gate approach? Remember, we want one and only one network to be conducted at the same time. Have you guys talked about doing this before? In 281?
Pull up and pull down.
Yeah, you pull and pull down, but compound gates or complex logic gates? No, okay. So here's the strategy. If we want to have a Boolean relation between X and Y, we'll assume there's N inputs, we implement Y bar in the pull down network. And we implement Y in the pull up network. But since it's made of P-channel devices, then we have to complement the input variables. Okay, so here's the strategy. We implement Y bar in the pull down network, we implement Y in the pull up network. Y and Y bar is typically expressed either in sum of products form or product of sums form. Does everybody know what we mean by product of sums form and sum of products forms? That's a 281 concept. So let's look at an example here. A exclusive OR B. That circuit that required 5 levels of logic and 22 transistors, was it? We'll express Y bar and Y in SOP or POS form. So if I express Y this way, this is now in sum of products form, right? And Y bar, I'm expressing as product of some form. So I've used De Morgan's laws to express Y. Well, I didn't have to use De Morgan's laws. This is the Boolean representation of the exclusive OR function. Then I used De Morgan's laws to get Y bar, and I chose to express this in product of sums form. I could easily convert this to sum of products form. I could convert this to product of sums form if I wanted to. So, we said we implemented Y bar in the pull down network. So A bar or B. So A bar or B will make this conduct, and A or B bar will make one of these will make conduction here to here. And if you AND them together, then you'll have a pull down network. But we'll pull the output low when this function is satisfied. Pull up network. A and B bar. Maybe I should do it here. So A and B bar. A and B bar. If they're both conducting, it'll be pulled up. Or A bar and B. So here's the pull-up network to implement this Boolean function. This is expressed in sum of products form, but I have to come up with the input variables. So this becomes A bar, B bar bar, B bar, and A bar bar, which is just B here, and this is just A here. So this becomes the pull-up network. Stack them on top of each other, and I have the exclusive OR function, assuming that the inputs are available, A bar and B bar. But they may not be available. We assume they were not available before. So if I want to get A bar and B bar, I probably need to use static CMOS inverters to get A bar and B bar. If I do this, I can implement the exclusive OR function with 8 plus 2 is 12, plus 8 plus 2 is 10, plus 2 is 12, 12 transistors, and 2 levels of logic. One level of logic to invert A and B, and one level of logic to get through this complex logic gate. So we made improvements over what we had before. The answer is yes. This circuit is a lot simpler than what we had before. Less levels of logic and a lot less transistors. Here I've expressed Y bar in a different way. Sum of products form now. And here's an implementation then of a pull down network from the sum of products representation. It makes no difference which form I put it in to form the pull down network. And it makes no difference which form I put it in to form a pull up network. I can mix and match these together. So these are different pull down networks. Those two don't look the same, do they? The two pull down networks. Let's look at this function here, A and B. That's also a little bit of a pain. We can build it with a NAND gate and inverter. 2 levels of logic and 6 transistors for the most basic 2-input non-inverting function. The non-inverting function is more difficult to implement than the inverting function. That's true in general. If you use static CMOS implementations, the non-inverting functions generally require more complexity and more levels of logic than the inverting functions. Let's look at this circuit right here. If A and B are high, these N-channel transistors will get turned on, and the output will be pulled high. But if A and B are both low, or one of A and B is low, there will be an open circuit from here to here, and the output will be pulled low. So this implements the to input NAND function, excuse me, it requires only one level of logic, 2 transistors, and 1 resistor. Is this a good solution? No. What's wrong with it?
The resistor?
Yeah, I got a problem here. That resistor might take up as much area as 1,000 transistors. So it appears that we're making progress, but maybe we took a small step forward and a great big step backwards. Oh, I can put the A input on the source of that transistor and the B input on the gate, and I can also implement this AND function. Now I have 1 transistor and 1 resistor. But again, we got that resistor there, that's a limitation. Now, we're going to show later that we can replace the resistor by a transistor. Our models we have right now are not adequate for doing that. But if I could replace the resistor by a transistor like this, now I'm reducing it to 2 transistors and 1 level of logic. We can't determine the logic levels here. We can't determine the power dissipation with the models we have currently. But we've got a circuit that offers potential for reducing complexity. You can show that this function implements this circuit implements the Boolean, the exclusive OR function. What do we start out with? 22 transistors and 5 levels of logic. We're now down to 2 transistors and 1 resistor. You can put the A and B inputs in as I've shown here with P-channel transistors, and again 2 transistors and 1 resistor. So this is past transistor logic. It's one of the other logic styles. It can offer significant reductions in complexity for some functions, particularly the non-inverting type functions. The resistors are going to cause a problem, but we'll talk about how to address those. The signal levels may not go between 0 and VDD. We'll address that issue. Static power dissipation not be 0. We'll address that issue. We have better models. Signals may degrade if we go through multiple levels of logic. We'll address that problem later. But the resistor is often implemented with a single transistor to reduce the area. So that will help overcome one of the problems. Past transistor logic is also widely used because in many cases it's got an incredible reduction in complexity. Are there any questions? That's all for today. Thanks.
I